I'd like to do a basic video on magnetodynamics, my apologies, magnetostatics, basic magnetostatics, and this is a teacher's resource video. Now, first of all, when I do presentations of that sort, I start off with my own personal introduction, because whenever I delivered a presentation on magnetostatics, it was in as a guest appearance. So I do personal introduction of postgraduate background in radiation physics, my interest in nuclear physics, and as well as the my background in astrophysics. So I then provide historical context. So I start off with the history, because I've studied history of physics and basic philosophy. So I provide a historical context for magnetism, where it started from, i.e. Greco-Chinese or Sino-Greek backgrounds, and I talk about the lodestone, hematite, and all these iron ores that depict or display magnetic behavior. I then discuss so I build my knowledge up from there, and I talk about, I try to, so after I've spoken about the hematite, lodestone, iron ores, magnetic behavior, I quickly jump over to home use, i.e. fridge magnets, just to give them, now these are, mind you, year 11 students, so they know about fridge magnets. So I talk about fridge magnets to orient them quickly over from historical context to daily life use. And so I talk about magnetization, and I say, well, not all magnets are like that. Magnetism is a phenomenon which is of around about 3 to 4 types. The first one is ferromagnetism, then you've got diamagnetism, then you've got paramagnetism, and then you've got anti-magnetism. And the most common one people understand is ferro, which is nickel, cobalt, and iron. But I tell my students that there are elements that are diamagnetic, paramagnetic, and anti-magnetic. So that being said, I then reflect upon the philosophical, the nature of magnetism, as a phenomena, and I relate it to electricity, E field, and I tell them that just like you've got electric field theoretics formulae, you have magnetostatic and magnetodynamic formulae as well that are similar to E field. And I state that magnetism exists, or is expressed by magnetic fields, and there are, just like there are electrons, photons, there are magnons that convey magnetic field, convey the magnetic field, which is denoted as B. So E for electric field and B for B field, and they act orthogonally to each other. So I then give them, they understand it, and then after that I discuss the anatomy of a typical magnet. And so after I've given them a bit of a outlook on what are the phenomena of magnetism, attraction, repulsion, laws of magnetism, likes, repel, opposites attract, E field, how magnets behave, paramagnetism, diamagnetism, ferromagnetism. I then discuss the anatomy of a magnet. I take this simple magnet, I label north and south. So bear in mind this video is for teachers, so I don't need to explain every single thing. Then I draw a typical B field. I draw it, and I let them know that in the forthcoming practicals they'll be spreading iron filings on top of a paper underneath which there's a magnet, and then the iron filings shall depict the B field pattern by arranging themselves on the axial vector axial vector look vector hang on axial vector projections of the B field. So that's pretty quick and simple. And then I say, you just don't have bar magnets. You've got horseshoe magnets, you've got circular magnets, and you've got disc magnets. Sorry. So, and a magnet may be of any kind, but the poles, it'll always be dipolar. It can be quadrupolar as well, but most magnets are bipolar, and there's no unipolar magnet, so you can get quadrupolar as well, but that's just a juxtaposition of two bipolar magnets. So quadrupolar are rare. Then you get superconducting magnets as well. So I'd say this is the basic anatomy of a magnet. And Earth is also a magnet. It's a spherical magnet with a north pole, south pole. I then state that this is the Earth, and so if we assume it to be the Earth, the North Pole's on top, quote unquote, South Pole's at the bottom, and then it acts like a B field. There's a B field, 55 microtesla, which is very, very small, 55 microtesla. So, and then Earth acts as a B. So the top part is North Pole, bottom part is South Pole. Now, what happens is there's a shift. Sorry, parallax shift. So it's changing, and the rotation, the time period is 10,000 solar years. So every 10 to the 4 years, the north and south get flipped. So I then tell them that the geographic N pole and S pole are not the same as the cartographic. So I talk about the geographic poles, cartographic poles, and I talk about the different kind of maps that exist, Gall-Peters, and so the three different kinds of maps. And then geographic pole is different to cartographic pole, and cartographic is a bit of a imaginative simplification, like equator, Tropic of Capricorn, Tropic of Cancer. So having said that, I then introduce the idea of compass alignment. So I say that there's an ore called lodestone, discovered in China, used in China along same time when fireworks were discovered, and this stone always aligns itself to the north, and the bottom part goes to the south as a default. So wherever the needle will always point to the north, and we during technological era we've devised two more directions, east and west. So by the rotation, axial rotation of the compass in response to the B field of the Earth, we can then find out east and west. And south will always be the 180 opposite of north. So we've done that, and then we talk about just like there's an electrical force, there's a thermal force, mechanical force. Just like that, there's a magnetic force as well. Now, magnetic force is on a magnetic electron or a particle, and it allows it to spin anti-clockwise or clockwise, and that spin is due to the action of B field via B force, magnetic force. So that's that, and After the compass alignment, I talk about magnetic force. I then remind them that in this chapter, there are about 3 to 4 practical investigations, required practicals. One with a paper clip and a magnet, the other one with the iron filings. Then you've got a few of the practicals that talk about the unbelievable, that talk about the how to check out the magnetic density and whatnot. So the 3 to 4 required practicals, I talk about it in slight detail. Probably draw a few tables or a few small diagrams on whiteboard and explain to them how each practical would work in about 5 minutes per practical. Draw the diagram, aims, objectives, and that's that. So then I'd conclude by mentioning that practical investigation is queued for next sessions, and we'll do about 2 practicals per practical class, and I'll demonstrate it, and then you can take down the readings. So I then instruct the students to, I then finish the presentation with about 5 links. 2 of them will be on practicals, and 3 of them will be on theory. So I want them to click on it and summarize what they learned and write it in the notebooks for me to mark next day. I collect the notebooks and then come back. Now, the next lecture will be about misconceptions. Misconceptions. And I would ask them to learn about the domain structure, the domain structure of the magnet, but ignore it. That's not non-intuitive, but ignore it. And then I would tell them a little bit about the quantum organization of the magnet, but and then refer to spintronics. And then again remind them about cartographic and magnetic poles, geomagnetic and cartographic poles, and then I'll tell them to remember to mention the polar deviation in both degrees and angular distance. So so if there's one cycle every 10,000 years and there's 360 degrees every 10,000 years, how much time would 1 degree shift take? So I then do that calculation, remind them about 2 pi r over t, and that'll be the the angular velocity. And then I would then go over this calculation, specify how long would it take for 1 degree, and then I would talk about the concept of radian, angle mapped as a unit of time, and that'll be the radial velocity, angular velocity, sorry. And then I'd like to specify magnets do not attract all metals universally, rather on contrary exhibit selective behavior. So then after I've done all of that, I'd slowly lead them over to ferromagnetism, paramagnetism, dimagnetism, and antimagnetism. So as I would call it, FPAD. FPAD. So I then specify which metals go for ferromagnetism, which ones depict paramagnetism, which ones are antimagnetic, and which ones are diamagnetic. So after having done that, ferromagnetism, paramagnetism, antimagnetism, diamagnetism, I would then go over my results for the practical investigations that I did with them. So I do about 3 practical investigations. After that, I would then discuss the results and then reiterate misconceptions. So after having done that, it would take me about 3 weeks worth of hard work, 3 weeks, around about 6 classes, and the topic is done. 3 weeks, 6 classes, topic sorted out, and then they can practice in their own time. Thank you very much. I hope you enjoyed my video. Please like, comment, share, and subscribe, and all the rest of the jazz. And if you've got any questions, technical questions, do not hesitate to contact me in the comment section down below. Thank you very much. If you've got any, so this was Magnetostatics. If you've got any questions about magnetodynamics, please let me know. Cheers. Take care. Bye now.